Ultrafiltration membrane, and it can filter stuff that is even smaller than the bacteria. It can filter things like viruses and pathogens that give you fever. The pore size of this is about 3 nanometers.
We developed a formulation that you can embed into a silica tape. You allow it to dry. You can wrap electrical cables with it. Our wire did not ignite is very beneficial because it will prevent the spread of fires.
And this is just a plain piece of aluminum you would find on power transmission lines. So the water droplet spreads on the surface pretty well, and it would form ice in freezing conditions. This is our technology here. Water droplet just rolls right off. So here we etched it, and then we coat it with a hydrophobic coating.
A piece of aerogel, which is one of these things, and then we load it with liquid fragrance. After that, you'll have something like this. You can have it like wrapped in foil, for example, and you can just unwrap it. You can have your fragrance right there.
Hi, I'm Keith. I'm in 4th year nanotech, and I'm with Uzair, Edgar, and David. And what we aim to do in the last few months is find a way to grab all the kinetic energy being wasted when people walk around in large public places. We created a solution where our only limitation is the size of our beaker. The way that we approach this is we're growing zinc oxide nanostructures on a copper substrate. Basically, for a few $100s, we've been able to create a lot of samples that can create industry-leading power numbers. So basically what you can see is if we push down on this, we're getting a very substantial amount of power on the ammeter over here. We've had on the order of 50 to 60 milliamps just coming from this really tiny sample.
We're working on a MEMS-based alcohol sensor. Right now, they're a really effective way of preventing drunk driving accidents and fatalities, but they're very, very expensive.
Some of the courses that helped us a lot were actually the microfabrication courses, which pretty much went over all the different techniques that are used to make these sort of devices. And also some of the photonics courses just last term helped in understanding the laser Doppler vibrometry that we use to find the resonance peaks for our device.
Well, it's really great just to be able to bounce ideas off of him. Like when we're thinking about something, like it might take a week or two of literature search for us to actually figure out whether it's possible or not, but we can go and talk to him, and he's got so much experience that we can just say, you know, will salt precipitate out our nanoparticles in water solution? It's a yes or no answer right away. Such a diverse range of material that we have to cover. We really have to be able to learn quickly and be able to talk to people to get the information that we need and interact with these like different faculties in entirely different languages of research, like from chemistry to materials engineering. And so when we're presenting to a group of people and we need to come up with this diverse project that impacts such a wide range of people, it's a lot easier to talk about that from diverse perspectives with the background that we have.
Are you prepared with an undergrad to go into a PhD?
With a degree in nanotechnology engineering, I feel very much prepared.
We're using a protein detection system with aptamers. The protein is PDGF-BB, and this has been shown in literature to be present in human blood in all cases of breast cancer from early stage to late stage. This is a murky solution right now that's both magnetic and fluorescent. This is a permanent magnet, and upon the binding of this too, you can see that very rapidly you have the solution clearing. And this is going to be used for signal transduction of a rapid system.
It was what I did at Mitsubishi Chemical in Tokyo, working on magnetic separation of proteins for biomarker discovery. And the work in the nanoscience group there actually led directly into some of the stuff that I'm doing here.
Our project can save a third of that, which is 5 million people. And the way we're going to do it is take it to the next level. And the 3 steps we need to do to take it to the next level is A, reduce the size of the particles to get more sensitive data, and then take it from a lab to an environment which is more like the actual blood we have. So we'll go into in vivo and take blood samples and do this in blood to test whether it still works or not. And we have high hopes of doing that.
So we're using a nanostructured material to scatter the light more effectively and allow the light to bounce around within the silicon and hopefully get absorbed more efficiently.
We've been working on creating a diagnostic biosensor. So it's a microfluidic device that detects glucose levels.
Our project is called Clarity, and what that is a super hydrophobic coating that can do anti-fogging that is both cheap, eco-friendly, and very long-lasting.
So a lot of the current coatings suffer from a problem that they oxidize extremely fast, and under UV they degrade. And there's a lot of application. You often have glasses fogging up, protective equipment fogging up, your windshield fogs up.
In normal bulk material, for any crack propagation, defects usually multiply and go to the surface, which facilitates plastic deformation. But if you go to the nanoscale, those defects can propagate at a much smaller distance to any free surface area, so therefore creating a pristine, almost perfect crystal. So as you continue to compress it, the material becomes more perfect and your strength actually increases. This is the first time that someone is actually doing it with an array of pillars and embedding it into a polymer matrix.
Because we can embed this in any kind of polymer setting, we can put these pillars inside helmets as part of the design, therefore mitigating the risks of concussion.
We came up with a three-step process, and this is what we've been working on for the last 2 terms. And so it's a 3-step process: electrospinning, stabilization, carbonization. And we start off with these pan fibers, and we use an electrospinner, and we come up with these electrospun fibers. And then we put it through the next step, oxidization, and we finally carbonize it, and we end up with this sample right here, and that's the carbon nanofibers.
The purpose of the project is for automated vehicle guidance, so essentially a car or a factory robot that could drive itself based on our paint system.
We're using super paramagnetic nanoparticles. Right now, they are not attracted to any metallic objects, but once we put it in contact with the magnet, it's completely magnetized.
I'm a grad student now at MIT, Department of Materials Science, and I'm working on tunneling quantum devices to make computers faster and more power efficient.
I'm now at University of Toronto, the physics department.
I'm doing my master's in mechanical engineering here at Waterloo. My research is on nanophotonic biosensors.
I'm trying to start my own venture right now in software.
One thing that I found we definitely got from this experience is that we have a broad knowledge in a lot of different areas, and so we're really able to connect things here and there, and still we have the ability to learn, so we can go more and more in depth. But the beautiful thing is we're really comfortable working across a really broad field of things.
I went to grad school in a bio field, unfortunately not a materials field.
Well, I'm applying to medical school, and I have 3 interviews. I'm going to actually go to one tomorrow, and I have my fingers crossed.
I've actually been accepted to work in a microfluidics group at the University of British Columbia.
I'm planning to go to graduate school, starting my PhD, and I'm planning to go to MIT, either mechanical or electrical engineering.
I will be using my technical experience hopefully at a startup in San Francisco. So I'm interviewing right now, and it's more like evaluating those startups. So they want someone who can understand the technology, how it works, and see how feasible it is, as well as the commercialization of that technology.
For us, I guess the main advantage of the nano program has been its multidisciplinary nature.